Okay, very good. Thanks so much, Roberto. Can you hear me? Okay. So yes, I'm Fabio. I'm a kind of a theorist. I'm a phenomenologist, really. And I guess for this month, I'm the closest person to experimental physics that you have met or you will meet, I think. And therefore, think of me as an experimentalist, okay, in first approximation. And so these lectures are somewhat meant to be uh, kind of practical, and I'll try not to give to do too many calculations on the blackboards, the least I can, and I'll make my best to chat and to give you a feeling of what we mean with collider physics. So who is working on collider physics among you, even indirectly, even like model building or anything that is related anyway with the physics? So it's a fair amount of people, very good, very happy about that. So the people, other students can also ask to their peers. So the idea is to give you an idea of what is a collider, how we do collider physics, how we extract information from very high energy collisions, and why we do that. Okay, so it's a big word with many exciting directions taken by a large community, and many directions are not being fully explored or even starting now. So I hope to talk to you today, this afternoon, tomorrow, and the next days, so that I can even tune a bit what I had in mind to do. And if there is anything that you are interested in knowing more deeply, or to know what's going on, you ask me, and maybe if I know something about it, I can also talk about that. So I will not say it's on demand because that would be maybe too much, but it can be tuned. Okay, so I will be very happy to have your suggestions along the way. Above all, if there are things or issues that you're not familiar with. So our goal is to give you a bit of perspective, to give a basic concept mostly, to tell you about the tools that we use in everyday life in collider physics, for example. So from the theory point of view, in the sense of making prediction for what we see at colliders, right? What we measure at colliders. And then I will focus on, as I said, a few sample applications on Higgs physics, on top physics maybe, and on BSM. So BSM, we have two main ways of looking for BSM and the colliders. One is indirect way, measuring, making precise measurement of observables that we can predict very well in the standard model and check whether there are deviations. Or the classical way, so to speak, is to find new particles, right there, like resonances or clear excesses in some observable due to resonant particles. So I will try to explain a bit both of them, even though I guess most of you are familiar. So for the course itself, I will use the Blackboard, and this is one of the traditional things of this school. I have also a few slides along the way in case I need some plots. There is also, I'll show you, if you go on my web page, there is links here, and there are two large sets of slides. There are many slides, okay, and I will talk about subset of this material, and part of it is what I call QCD, because QCD is a very important part of the LHC physics, right? So we need to understand how it works with collisions from QCD point of view, at least for PP, but in fact also for E plus E minus, for example, collider. And then there is a set of slides on BSM, and which is a review of the standard model plus EFT theories, for example, and searches for new physics. So there are also a set of exercises in QCD. These are more technical in case you want to try them. And then, as I said, I might do a few computation on the Blackboard. One of them I think is particularly interesting, so I'll try to do it. Anyway, it's a bit heavy, so I hope tomorrow, if we do it tomorrow on Friday or Wednesday, you'll bear with me. But in case you're gonna get lost, there are mathematical notebooks where all the calculation is done, right? So then you can check all the details there with the Mathematica. So who is using Mathematica? Okay, so and that's not a problem. Okay, is that good? Do you have any questions about that? So the material goes is really a choice, right? Of a selection of this material. Okay, very good. So let me start with very basic, right? So we start very slowly, and what I want to start with are accelerators. So there is a long story of accelerators, right? We are in a phase. So let me put this up. As you know, we have a story which goes back to the 60s. So the idea of an accelerator is the fact that if a particle is charged, then we can accelerate it. So there are two ways of accelerating it longitudinally, right? So the electric field, like in a capacitor, where you put an electric field, this we learn very soon in school, you put a charge, and then if there is an electric field, the charge gets a force which is proportional to this charge and to an electric field, and then is accelerated really in the sense that its velocity, the module of the velocity, the speed is increased. But there is another way it can be accelerated, which is through the fact that in a magnetic field, as we know, a particle can be deflected with a force which is perpendicular to its velocity, and this is due to the magnetic field. So a particle in a magnetic field follows a trajectory which is circular, right? If composed, can be helicoidal, but that's the centripetal acceleration. Okay, so remember, electric field increase the value of V, magnetic field turn the particle around. So how the first accelerator was built? Well, the design of a first linear accelerator was very intuitive, right? You had some kind of electric field in sections which were increasing in length. Okay, so the length was the length of each section of field, electric field, is increasing. And then what you do, you give you give an electric field which is alternate. Okay, so here you have an electric field current, and so yeah, this way. So the one of them is attached here. So all these have and then this goes here. So alternatively, right, you put in one polarity and the other one in the other one. So they are oscillating, and you accelerate the particle with the time, which is the time of the RF, and then the time is the distance divided c, the velocity, and you get the d is equal b, the velocity, the lambda, the length, the wavelength of the oscillating field. Okay, so you reverse the oscillating field one or the other, but every time the particle passes through, right, it gets a kick on the same direction. So this is was invented in 1928. Okay, so almost 100 years ago. And then after this scheme, right, this scheme gets complicated. If the particle is relativistic, right, the alternative current has to be retuned. So the idea was, and of course, then you need a very long length. And this problem remains, if in some sense. So if you have a linear accelerator, the problem remains that you have to accelerate the particle in a very short time. This is also a scheme somewhat that is there for the linear accelerator, even though it's slightly different. And then the other way of accelerating nowadays is what we call a synchrotron. So the scheme that we use now, also this you might be familiar. So a synchrotron is an accelerator where the orbit of the particle stays the same. Okay, so we fix the orbit, and what changes is the B field. Okay, so the idea is the following: you have the radius is P over B. So P is the momentum. So you raise the momentum, and then proportionally you raise B in such a way that the R is the same. Right? The idea here is that what we learn again, right? So, right, the kinetic energy of the particle divided by the ratio. So the acceleration, the centrifugal acceleration is the force, okay? And then you get this equation that tells you that if you increase the momentum, you have to increase B if you want R to be the same. So you accelerate the particle, okay? So here in the straight line, so in the region where it's straight, you accelerate with an electric field. And in the region where it curves, you use a B field to curve it. So a normal accelerator, like the one we use, like LEP or LHC, has regions where the particle goes straight and regions where the particle are curved. And so this, the region where it's curved, of course, have a radius which is smaller, typically, than the effective radius of the ring. So when we show that LEP is a ring, right, the tunnel of LHC is a ring, it's not really a ring, a circle, but there's regions where it's curved and regions where it's straight. I'm saying this, you should keep this in mind because for some new futuristic accelerator, the proportion of space that you leave in the accelerator for curving and for accelerating is critical to reach the higher energies. In some very futuristic ones, linear part can be even problematic for radiation, as I will mention later. So it's important to know that both these parts are important. So again, the way we think is that once we increase the energy, we tune the B to match the momentum which is given here to curve the particle with the corresponding force, curving force. And then and the frequency also of the cavities, so this is the speed. So this is the frequency. So the frequency which I use here to accelerate is also to increase with the speed, right? Because the faster goes the particle, the change in polarity you need from one to another. Okay. So this is the idea of an accelerator. Why I'm saying that? Because it turns out, as I said, that we are very sensitive at the end to the to the design, right? The other thing that is important to recognize is that, of course, the higher the energy we want, the larger has to be the B field in the dipole magnets. So there are various kind of magnets. One, there are so-called quadrupole magnets to focus the beam, but there are also dipole magnets, which are here to curve the field. Okay, so you see that now there is one obvious issue, is the fact that we want to raise P, we have to raise B. But B, unfortunately, we cannot raise as much as we want. Okay, and the reason is that B is limited now of order of a 10 Tesla, let's say. Okay, so the technology that we are able to deliver right now is with superconducting magnets, and the order of magnitude of the field in the dipoles is order 10 Tesla. So an LHC now is 8 Tesla. Okay. So with 8 Tesla, we can arrive up to 7 TV for each beam. And the largest magnet which we will have at LHC right now will be between 11 and 12 Tesla, which are being installed now. And these are not dipoles, actually. These are focusing magnets, or quadrupoles, which have the current record for the magnetic field. So this is a critical quantity, and there is a lot. This you will hear a lot if you listen to again what we will be doing in the future and so on. Because depending on this figure here, we can reach. So this is really related to the maximum energy that we can achieve in a given collider or given radius. So I have two choices. Either we increase the radius, okay? Either we increase it, or we increase B. We have no other way. So for the future collider at CERN that we are designing, we are actually doing, we foresee to do both for PP collision, to increase the radius, right? So it will be 90 kilometers long instead of 27 currently. Okay, so 3 times longer. And then we also would like to increase B. Okay, but the current technology, as I said, arrives at 12. So we are hoping to get to 14 Tesla or higher, right? So there is an whole range of R&D here. R&D means that we don't know how to do it right now, okay? So we are studying them, okay? So there are various technologies under scrutiny, various materials, and it's a very active line of research. The reason is, right, that if you, it's obvious, right? I mean, if you can increase this, then you have not to dig a much longer tunnel. So, right, and then if you're thinking about money, that most of our life is measured upon that, right, most, or a fair fraction. Then, of course, it's better to invest in R&D and get this higher Tesla than having to dig a very long tunnel. Okay, so what is the idea of a synchrotron? What is the other point which I didn't mention? Well, the other point is, of course, that we accelerate particles for them to hit a target, right? So collider specifically, by the name, it means that is a machine where particles collide head-on. Okay, so we have two types of collider, two types of accelerator experiment. We have what is called a fixed target experiment. So class 1, and then we have collider. So we learn very quick, very soon, right, that which one, So which one is best? So if you want to study fundamental interactions and you want to search for new physics, which one between fixed target and collider you should choose? Who says fixed collider? Sorry, that would be a convenient answer. Who says fixed target? Oh, okay. Who says collider? Fantastic. So you're a bunch of biased people, right? And I am one of you, right? And not telling it's only you. So we are biased because when we were kids and our parents brought us to listen to seminars, every time, right, we are being told, colliders because the higher energy, higher energy. Wait, right? Wait. It's not the story is a little bit more elaborated than that. Okay, so why you all answered colliders? Well, because when you calculate, right? Remember, right? You have a beam of energy E. You collide with a fixed target, right? And what happens is that the available energy in the lab only scales as 2ME, right? Where M is the proton, let's say, right? So it scales with the square root of E. And the reason is very simple, because you have a booster, right? Your center of mass is boosted. So your event here will also be boosted. So when you go to the center of mass frame, you get 2ME. So you do a simple, right? You calculate the center of mass energy, and you find that it scales with ME. While if you have a collision, head-on collision, the energy, right, of the center of mass is to the energy of the beam. So the energy available in the center of mass for the collision is proportional to the energy of the beam. It's really like a car accident. It's not different in any way. So the available energy grows linearly with the energy of the beam. So obviously, right, and then why we all answer colliders? Well, if you want to go higher energy, you choose a collider. That's clear. No doubt about that. But what is the problem of colliders? So everything has always a dark second side, right? So energy, check. But what is the other figure that we will discuss a bit more in detail in the following that is a figure of merit of a collider? The luminosity, but so how many events you produce, right? I mean, if you have a fantastic high energy collider, then you get one event, and that's it, right? You'll not build a very large statistics, and then it will be a bit difficult to make any study. So the other figure of merit is the number of events of collisions, right? I call it event a collision, right? So this is another figure of merit. So which one here is the best? That's intuitive. Very quickly, you realize that fixed target are better for luminosity, right? Because here, right, you have to have a bunch of particles colliding with bunch of particles and they have to find each other. On the other hand, if you just have a beam against the target, you take a very dense material and then you hit the target, so to speak, all the time. So the number of events is much better than fixed target, okay? So fixed target and colliders are actually complementary. And that's the reason we are still doing fixed target experiments. We're not stopped after we invented the colliders. I mean, fixed target experiments are running all over the world, right? At CERN, at Fermilab, and so on. And And these are interesting because you can produce a lot of events. So if you're looking, so I said, if you're looking for new physics, then you have to say which new physics, right? That's the usual thing, right? So there is new physics that we expect at high energy with heavy particles, for example. Then the only way is a collider, obvious. But there is also new physics that might be lurking here, there, which we don't know, which has lighter particles, but which are what? So why we haven't seen them if they are light? What is the only, so how light particle might exist and we have not yet seen them? They have very small couplings, right? They are very weakly interacting. One of these particles maybe is dark matter, for example. Maybe dark matter, some dark matter candidates are very light, are very weakly interacting. Therefore, there, I don't want a collider, or, you know, I might also want a collider depending on the detail, but for sure, I also want big experiments, right, with very big fixed target like Camocande, right, where it's a huge fixed target experiment, if you want, where there is no beam, it's not an accelerator experiment in that case, but where I can maximize the probability of seeing something which is light, but has very small cross-section. Okay, so there are two figure of merits there, and collider builds upon the idea that I'm looking for something heavy, new and heavy, or in any case, I want to study the properties of particles which are heavy. Heavy means, so just to give you an idea, now I'm using heavy. So for me, heavy is the vacuum expectation value of the Higgs, so that we know what we are talking about. If you ask some of my colleagues, heavy will be something else for sure. But let's say, you know, V, which is vacuum expectation value of the Higgs. What? Okay. Okay. So so heavy means order of the 250 GeV or 1 TeV, let's say. Okay, order of magnitude. So if I want to study the states which are this heavy, then I need a collider. Okay, that's the way it is right now. Okay. So in fact, it's interesting to see that historically, right, the way we have discovered particles in the Standard Model has followed really the pattern of the energy of the collider that we built. Okay, so there is not by chance a one-to-one correspondence among our ability to increase the energy and our ability to actually detect what were there new particles, because we didn't know that they existed. But that's the idea. So that's the idea we were grown up with, okay? And the reason why we have been doing this in this scheme, and actually, if you look at it, and now I will talk about in a second, even the type of collider has been kind of alternating. I'll explain it in a moment. But if you see the increase of energy, right? So these are the masses of the particle. And so let's remind ourselves, right? The B meson is amount 5 GeV, right? So before that was charm, tau, the B, W and Z around 100 GeV, the top 200 GeV, and then back to the Higgs 120 with LHC. So for each collider, basically for each, almost for each proton collider, we had a particle discovered of increasing mass. We are so used to that, right? And why we are so used to that? Because in fact, we knew that these particles were there, and therefore we built the first collider which was at our disposal with the technology to reach that energy. Okay, so the history of collider followed the building really of the Standard Model. Not by chance, right? It was done by design. If you write the Lagrangian Standard Model, which we will discuss more and more in the coming lecture, you see that there are regions, sectors, entire sectors of the Standard Model that have been studied at different stages of collider. Okay, so for example, again, the typical example you will learn, right, that you have witnessed yourself is the discovery of the Higgs. And the discovery of the Higgs was the last thing, because the Higgs is the heaviest and somewhat the most difficult to see because of the way it's produced and it decays. Okay, the way it interacts, the Higgs is difficult, and that's the reason why we had to increase the energy, to increase the number of events, and once we had enough events, we were able to see it. So it follows this logic, which you can follow in history like that. So now you might ask, right? So which particle I should use to build a collider? So what particles are the best? Well, the answer is easy, right? Because you look up in your PDG and you find which one. So you understand, right, that these particles have to go around a long time. You have to keep them, move them, and so on. So the first condition that you must have naively for a collider to work is to choose particles which are charged. Thank you. Yes, excellent. And then, what is the second condition? They are, well, they have to be long-lived, right? Enough, because otherwise, so let's say stable. Okay, so charge is stable. We are down to very few, right? That's cool. So proton, electrons, and what else? Neutrons? No, not good, because they're long-lived enough, let's say, but they're not charged, so neutrons are not good. What else? Muons? I'll talk about that. Then what else? Positrons, thank you. Antiprotons at this point. And then what else? There's something glaring missing. Ions, right? Nuclei. Right? Ions are good because neutrons in the nuclei is stable, right? Is a big object actually as a ratio, right? So it's very heavy with respect to the charge. Okay, so it's a bit more difficult to bend, right? Because it's heavier. So the rigidity of the magnetic field depends on B and the radius. So the energy I can reach is lower because they're heavier in the same ring. Is that clear? It's just an inertia thing. So the energy I can reach is lower, but still I can accelerate them very efficiently because they're very much charged. Okay, so ions are possible also because they have neutrons inside which are stable. So they're clever beams, ions. But they are more difficult to turn, so the energy is lower. So, for example, what is the energy at NHC for ion, like lead collisions? Do you remember? Do you know? It's a bit smaller, right? It's 5 TeV. It's not 14 TeV. So we collide ions at lower energy because of this inertia thing. So we don't have much choice. So let's say that, so let me leave out the ions right now because they are somewhat similar to the protons in the way we handle them. So we have protons and electrons. Okay, very good. So if I need, so I need to produce, right? So if I want a collision head-on, I typically need what? I need to accelerate one beam in one direction and the other beam in the other direction. So what do we do normally? Well, instead of scattering particles, we scatter particle and antiparticle, because in doing so, I can accelerate them in the same beam pipe. Is that clear? Because with the same field, they turn in the opposite direction. Okay, because the Lorentz force has a sign in the charge. So if I have electron going one way in one beam, okay, in one beam pipe, then the positron go in the other direction. So I let them miss, and then I let them collide where I want. Very, very easy. Okay, so this is easy, the part of acceleration. What are the problems here with electrons? Let's see. What are the downside of the electrons? First of all, very good. Okay, Brem, I'm coming to that. So why Brem? Because it turns out that a charged particle, so let me write the formula here so I don't get it wrong. So irradiated power irradiates with power with the following formula, which is called linear formula. Which is, so beta is the velocity, right, the relativistic one, so is P over E, okay? So the dot means the derivative. So we all know, right, and this is one of the first things that we learned when we studied the Jackson, an accelerated charge emits radiation. Okay, so this is actually a basic principle of all the week, because we will use this principle over and over again. To understand colliders, actually, you have to have very clear in mind that an accelerated charge emits some kind of radiation. If it's any charge, not only electromagnetic charge, if it's a strongly interacting particle, it will emit gluons, let's say, strong interaction mediator, right? And if it's an electroweak charge, it can also emit electroweak bosons, okay, if it's accelerated. So this is a general principle which is true. So this is a classical one, not quantum, let's say, is still relativistic. So gamma is the gamma factor, okay, acceleration. So gamma is 1 over square root of 1 minus beta squared. And then you see, right, that there is this gamma thing. Gamma measure the ratio between the energy and the mass. So if the energy is a very relativistic particle, gamma can be very, very large number. So so this thing here, gamma, scales like energy over the mass of the particle. So at given energy, a light particle radiates a lot, right, given the same beta dot. Now, this formula is interesting because it has the linear part in the acceleration, but also the centripetal part from here. Okay, so this is the centripetal term, okay, which is, and this is the variation of beta longitudinal. So you see that if the particle is not changing beta module, but is only changing in the direction, you get beta dot times 1 minus beta square, which cancel 2 powers of gamma here, and you get a scaling of the power of gamma to the fourth. Okay, I repeat, if this is in a circular motion, you get 1 minus beta square times beta dot square. These cancel 2 powers here, and you get 1 beta point, which is an acceleration. Okay, so you, at the end, in a circular motion, it scales like gamma to the fourth. So this is what you were saying, the Brem. So Brem means that the lighter is the particle, the higher is the radiation. So now, if I put numbers here, I'll try to put numbers every time I can today. So if you put numbers, you get that at 90 1 GeV in the center of mass energy. 91 is the Z mass. This was lap 1. You get that the energy radiated over the energy is order of 0.3%. While already at 200 GeV, which is lap 2, the energy is 3%. So 3% is a huge loss, right, per turn. So it means that every time you have to kick it back because it's a radiated large energy. Okay, so these are two consequences. First of all, this is not very green, right? Because every time, every turn, I have to get back the energy. The energy is radiated. So unless I have a very clever way of recovering for this energy to heat building or so on, I'm going to lose that energy. Okay, so this is certainly not a very green way of accelerating particles, first of all. But second, and intuitively you get immediately that if you have to recover every time to give an energy, the fact that actually the accuracy with which you have the collision energy, the tuning of the center of mass energy, is very, very difficult, right? Because every time you have to radiate, every time you have to correct, and I told you there are regions which are curved and rectilinear. So before it collides, you have to correct the energy. So to correct the energy, you have to measure it and correct it before it collides. Otherwise, the collision will not be at the energy that you want. So your precision in the beam energy, in the calibration of the energy, degrades. And if you want to be, for example, on the Z peak, then it's much more difficult. Or if you want to go very close to a threshold to see what changes when you open up a production mechanism, then it's also difficult. Okay, so when you have a lot of radiation, also your accuracy in the beam calibration gets worse. So that's one problem. The other problem here is which one? Well, is an intuitive one. I have E plus to produce, right? I have the E plus I don't buy at the market, right? I have to make them. So I have to make a collision, right? Produce E plus, E minus, collect the E plus, collect them in a way that they don't annihilate with that, and so on. And then you have to cool them. Cool them means that you have to put them in the same beam and then accelerate them and collect them in bunches to then collide with E minus. Okay, so this has to be done and it's expensive. We know how to do it, but is a limitation to the what is called luminosity, right? The fact are coming soon to that definition proper, but is a limitation to have many E plus and E minus in the same bunch. So what is the alternative? So how I solve both problems? Well, I solve both problems if I, instead of colliding E plus, E minus, I collide P and P, or E and E. I could also do E and E, E minus, E minus. But to do that, can I do that? Yes, but I need two pipes now, because I need two magnetic fields on the other, orienting the other way, and that's the reason why the LHC actually looks like this, the magnets. The proton don't run, the two beam of proton don't run in the same beam pipe, right? They run in two different ones because they need an inverted magnetic field. So this is good. Then protons are easy to do. So this will increase the luminosity, okay? Because I can put proton and proton together, no problem. And why? But then I lose something, right? Why we are doing E minus, E plus, and not E minus, E minus? because then I could have done the same here, right? I mean, maybe I solved the problem of luminosity doing EMI. Well, that's rather obvious, in fact, because we are interested in processes which are mediated by annihilation of a plus and minus, while an E minus E minus will only do scattering through T-channel exchange of a boson, and therefore will not, for example, fuse into a Z boson or a Z age and so on. So it's really dictated by the physics. So why we don't have this problem for protons? Why we lift this why at LHC we run PP? Well, we run PP because of this reason, and because, why? So why we don't have this problem of annihilation? Say it again? Exactly, thank you. So there is a lot of stuff in the protons, which is correct, right? And that's why we call protons bag of particles. So we'll come back to that. It's very important. It's actually absolutely non-trivial that this is the case, even though we are so used to it that we don't even appreciate the fact. But okay, in the protons, right, we think of them as bags of quarks and gluons, right? Both quarks, antiquarks, and gluons, to be precise. In fact, it turns out that if you have a very high energy, the number of quarks and antiquarks are similar at the end in the proton if you look at them not with too much energy with respect to the original beam. So I'll explain to that, but basically, in some sense, right, there are a lot of gluons, a lot of antiquarks, and very high energy. So I don't really care, in first approximation, whether this was a proton or an antiproton, because I still have antiquarks there, okay? So that's the reason, and we'll make this statement precise in the following. But this is the idea, so I do proton and protons. Very good. So what do we need to worry about radiation at this point? Well, we take an immediate check, right? So a proton, mass of the proton over mass of the electron to the fourth power. So this is the gamma factor. The ratio of the gamma factors go with the fourth power of the mass. So I take the ratio, right? And this is 2,000, right, to the fourth. So it's a huge number, right? Is 10 to the 13, let's say. And then that's the reason, that means that the protons and the same energy as the electron radiate 10 to the 13 times less, okay? So almost nothing for what, for the beam energy problem. In fact, when we shoot our technology to the limit, as we will be doing, for example, in the FCC age, and the future machine that we run around the 100 TeV, and the protons will be very energetic. The radiation from protons will actually start to be a concern. That's interesting, right? Even though it's much smaller, not because of the energy of the beam, but because the radiation, the proton will emit radiation, okay? And this radiation will warm the superconducting magnets which are bending them. The magnets at LAMP, the bending magnets are not superconducting because the energy is very low. So we don't need superconducting magnets at very high V. But LHC, we need superconducting magnet. And if the protons themselves start to radiate, they will warm it up. So all this radiation has to be taken out. So you have to continuously cool down the system. So it's much more green from the point of view radiation, in the sense that you don't have to accelerate, but you have to cool the cooling system, so to extract heat from the cooling system in a very efficient way, a very low temperature. So it's very hard also, it's very energy. It can be very energy demanding. Okay? So now what I want to do with you is also, as I don't remember, who was mentioning muons? Who dared? Who dared to mention muons in my presence? Okay. So now, crazy ideas are what we strive for, right? I mean, I urge you to spend a reasonable amount of your time, which is proportional to the probability of success, right, on crazy ideas. Okay. So what about muons, right? What about muons? So what is the lifetime of a muon? Wow, great. Correct? Okay. So 2 times to the minus 6 seconds. This we know, right, because we compute gamma in school, which is gf squared mu fifth power, remember? Then there is this funky number below here. So this is a weak decay, right? There is gf squared, so it's m suppressed by the mass 5 times, and so that's the reason why the muon is actually another log lifetime. So let's see. If I have a muon and the energy of 1 TeV, okay, gamma is 1 TeV over 100 MeV, right? Mass, so let's be precise. Okay, so just to remember. So the muon mass is around 100 MeV. So this thing here is 10 to the fourth. So its lifetime, so I hope that's clear, right? This is the proper time of a particle. Then we know from Einstein that if it moves, it lives longer, right? How much longer? How much longer? It's gamma tau, 0. Okay, so I just need tau. So this lives for 20 milliseconds. So what is the distance that a particle living 20 milliseconds will travel for? Is c tau. And this is 6, so 3 in 10 to the 8 meter per second, 20 in 10 to the minus 3 seconds. And this gives 6 in 10 to the 6 meters. So it's the radius of the Earth. Okay, so remember, a muon of 1 TeV travels before decaying an average of the radius of the Earth, right? So if the Earth was not opposing any resistance, right, it will just go to the center, typically, of the Earth. This is a good way of remembering. And therefore, if I put a muon in the LHC ring, which is 27 kilometers, it can do about 200 turns. So please check the numbers, because I got the numbers yesterday, and so check them. But basically, it means that a muon with 1 TeV actually could run 200 times in a circular collider, okay? Which is right. If we are very good accelerating it, it's not that actually that of a problem, right? Yeah. Say it again. No, okay, yeah, you're talking. Sure. Absolutely. Yeah, yeah, absolutely. Yeah, yeah. You have to get there. You have to get there fast enough. Right. Yes. Yeah, but this is a detail. No, it's not a detail. It's the whole thing. So you produce a muon. Again, you need some kind of method to produce a muon pair. Then you collect the muon plus and mu minus from 2 sides, and then you have to accelerate them and cool them. in a very short time. Okay, but imagine that you can do it linearly, so to speak, or almost linearly in a very short time. Then you can put them in a possibly smaller ring, right? The smallest the ring, the better it is. So the Mu collider, if you think about it, is the only. So I don't know if you ever seen these schemes of collider, right, where there are, successive rings and then a linear injector. So like protons are collected, then accelerated, a bigger ring. So they go from PS, SPS, and then in bigger and bigger rings. Muons will do the opposite. We just accelerate them in a big ring, and then when they're ready, you put them in a small ring because you want them to turn many times, right, before they decay. So you would have a larger ring where you accelerate them, and then when they are ready, you put in a smaller ring where you collide them. So you would do slightly different from the other accelerator because exactly of what you're saying, that you have to very fast accelerate, cool them, and accelerating and cooling can be done, most of it in a linear way, and then you start accelerating them in rounds. So is this science fiction? No, it's not, right? It's not Star Trek kind of thing, in the sense that there is a bunch of people who are looking into this. If you are connected to the high energy community, even for the snow mass process a few years ago, there was a big statement, right, that this might be one of the opportunities that we have to do future colliders. Okay, why? Again, because if we manage to run them, accelerate them as we suggested, and collide them, then we certainly don't have the problem of radiation. Again, that's a factor 200 now, but to the fourth is enough. So you can put in a circular collider and accelerate them to the TeV, like we do with protons. So that is very similar to protons. But what is different with respect to protons? The muons are not a bag of particles, right? So muons are really something like point-like particle, so they behave like electrons, but from an accelerator point of view, they behave like protons, right? So I don't have this radiation issue. I have others, but not this one, okay? And that means that I can also think of processes which can use all the energy of the muons in annihilation in the final state, which is never the case for protons. Protons are bags, and the energy of each collision is the energy of the component of the bag, not the full bag, right? So the effective energy exploration of a proton collider is lower than the nominal energy in the collision, because each component is only carrying a fraction of the total energy. So the muons, if we are able to prove that we can do the acceleration in time, would be something completely new with respect to this scheme that I was telling you before, where I basically had E plus E minus, PP bar, PP, and then composition like P electron, right? So it will be completely new regime where truly you would have a collider which is in between, right? It's neither EE, is nor PP, but this new thing in between. Okay, so that's interesting, and something that many people are looking at, and there will be a 5 weeks workshop here in GGI in the summer on Mu colliders, right, with all the community, many of the representatives of the community who are interested in this option. Okay, are there questions? You can stop me any moment. So I'm going very basic. I'll keep going basic for the rest of the lecture. So now I want to be everybody to be on the same page, right? So now we write the master equation number 1 for accelerators collisions, okay, which is the one which has been already mentioned, which is this one. So it's simple enough. We are all happy. So the number of events, the number of collisions is proportional to the cross-section where the physics lies, okay? So I'll come to how we calculate this. I will summarize. I assume you know already how to calculate cross-section. I'm not explaining this. And then this one, which depends on engineers, right? So now I ask, which one do you prefer? And of course, so to be fully respectful, let me start from the engineer size. So the luminosity, so you see, remember that the cross section, so this guy is adimensional. This is like a number, right? So sigma has dimension of yeah. Easier way. The easiest way of saying what are the dimension of a cross section cross is a L squared, right? Is an area. And then this one, therefore, has to have dimension L to the minus 2. Okay? So, of course, these are, at the end, is adimensional. Okay, so the luminosity can be expressed in a geometrical way. So, what we is an intuitive way. So we have two bunches of particles that collide. And in each bunch, there is LHC, for example, there is order 10 to 11 proton. So it's a lot of protons, okay, in each of them. And they are squeezed to a very small section here, okay, around hundreds of microbar, microns. And so the luminosity, so this geometrical factor will depend on how many protons there are in the first bunch, how many in the second bunch, how many times they turn around, right? The frequency when they cross, okay? How many times they cross per second. Then how many bunches there are in the accelerator, okay? And finally, by the area, okay? So these, you see, these, so sigma is the, the opening, the sigma of a Gaussian line, how big is the radius in the x direction and how big is the radius in the y direction. So this is a length, so this is length squared. You see, however, there is a frequency. So this object is actually an instantaneous luminosity, okay? So this is instantaneous because it's per time, okay, per second. So to put, is not this one, because this one is integrated in time, right? Because it has not, there is no time here. So this has an instantaneous value. So now we put numbers. I said this is order 10 to the 11, 10 to the 11. Now, what is the frequency? And then let's see, the frequency is 1 over 25 nanoseconds. And how many bunches do you think LHC has in the ring? order. You know, if you know, I mean, you cannot, either you know you don't, right? But if you had to guess, 10, maybe, right? It has actually 2,800, right? There are a lot of bunches in LHC. So there are many bunches, just one, like a train, right? There is two trains of bunches that are colliding. And then what we said is that this here is ordered 10 to the minus 2 centimeters, each one of them. Okay, so if you put all these numbers together, I'll let you do it, but I did it, so please correct if I got something wrong. You get something like 10 to the 34 centimeters to the minus 1 times second, which is also easier to think in terms of Earth over nanobars. Okay, so what is a barn? So a barn is the unit of cross-section and is 10 to the minus 28 meter squared, or 10 to the minus 24 centimeters squared. Okay, so this is a good number, right? This is an easy way to think about it, actually, better than this unit, because it means that this luminosity with a cross-section of 1 nanobar, you get 1 event per second. Sorry, 10 events per second. Okay, so it's an easy measure, right? So then what you do? How many events you get in 1 year? Well, you multiply so by the seconds in 1 year, right? And remember, the second of 1 year are pi 2 to the 10 to the 7, to remember, right? Roughly. So then you get the number of events per nanobar of cross-section. So you measure a cross-section in bars, nanobars, picobars, what you like the most as a unit, and then you can tell how many events you have per second. Okay, so that's I will use this one now because it's easier than using centimeter square. Okay, so also so now let's see. Let's get a number, an easy number. No, so this I keep. So let's see. So let's get a feeling about the cross section. So now it depends on how big are our cross sections, right? If we don't have a clue, then this estimate is not very useful. So let's start with the easiest one. So if you have two protons, right, that collide, right? Remember that the proton radius is about 1 Fermi, which is 1 over 200 MeV, more or less. So if you look at the cross section from the geometrical point of view, this will be 1 Fermi squared, right? If the protons were disks, you just get this cross section, which is order 30 millibars. So order 10 millibars, okay? So the proton-proton collision is order of 10 millibars. So then you have the number of events will be L times sigma. So you get 10 Earth over nanobars times 30 millibars, and that is 1 giga per second. So you would have 1 billion events per second, roughly. So a huge number, right? I mean, if each of them, so one event in the LHC is about 1 megabyte of memory, right, to register the event, to record the event. So you would have an enormous amount of data to collect. Fortunately, or unfortunately, depending, only small part of it is actually interesting, right? So experiments have a system which is called trigger, which makes a pre-selection, automatic pre-selection on the hardware, so that is the hardware itself knows so what if an event is interesting or not. Okay, so the LHC will only typically record 1 over, some fraction of the events that are produced. Okay, so it's much more important to identify if an event is interesting than recording it. Now, you could ask, yeah, but I mean, maybe I also want to study some of the events which are very common, but if I'm throwing all of them, then I zero, right? So this is called pre-scale trigger. So you can also take one less interesting event every 10, right? And you can do this. So you pre-scale the trigger. That's also possible. So don't think that we are really throwing away all the events which are non-interesting. We are just taking less of them. Okay, enough to do a study, but most of them we throw away because there are too many for what is our purpose in any case. But there are, even nowadays, there are some kind of events that before we were not able to record, and we are recording them directly from the machine on tape. And this has been, for example, in B physics, right, but in B meson physics, we are doing this, and with an enormous success in the number of studies that we are able to do. So this is very flexible, but just to say now that the events that we are interested in are a small fraction. So now let's have a look and develop an intuition of, yes. What is the rate on which I can take something or throw it? Ah, yeah, very good. Thank you. Yes. Yeah. Yeah. So very good question. So how the trigger decides what is interesting? Right. Very good. Is that your question? Very good question. So there are various ways. Okay. But one easy way is to check whether in the events there are particles that come out at high PT. Okay, a very, very energetic particle. Because most of this interaction, nothing really happens. I mean, the protons scatter a little bit. They might even scatter elastically, right? Just go forward. Or maybe they break, but nothing really happens. Are like, tangential kind of collisions. So the typical measure that you can have, the simplest one is what is called HT. And HT is the scalar sum of all the transfer momenta in the event. Okay? So I see the tracks that go out in the detector, and I only measure the transverse component, which is the component which is perpendicular to the direction of the beam. So if a particle goes out this way, I only take this one, the transverse component, and I compute on the fly for example, all the tracks. In fact, it's not true. What we are doing, we are using the energy in the calorimeter, but it's similar, right? It's the energy deposit, transverse energy deposit in the calorimeters. So you sum them, the modulus, right? So you don't care about the direction. You sum somewhat the total energy, which is in the event, right? And then you say, let's say that this is bigger than a threshold. Okay, and then you play with the threshold to get the rates. right? So you look and try to make the threshold as low as your computing and data acquisition system is able to get data. So you tune it to the maximum of your capacity, okay? And the more energetic is an event, the in a PP collision, in a PP collision. In E plus, E minus collision, you read them all in first approximation, right? There is no trigger in E plus, E minus. Again, it's a bit rough. There is some, but it's a completely different story than in PP. PP is so large a cross section that you have to have a trigger. In E plus, E minus is so small that you just record everything. Okay. Any other very good question? Yes. Yeah. Right. So in fact, what we do, we build proxies, right? So we don't reconstruct the whole event because we will not have the time, okay? But so we have a coarse. So the first level is very coarse, right? Very coarse. You use the calorimeter. You just look how much energy is in the calorimeter, which is very fast, and then you decide. Then you can go in levels, right? So you keep this, and then out of this, after you apply something more refined that takes a little bit more time, right? So you build a pipeline, and the important thing is the time it takes each one into the pipeline and the number of pipelines that you have. Okay, so it's a dynamical system really, right? So you get out one, it passes the first one, it goes into the second level. Now the input of the second level is much lower in frequency, and I can apply a concept that, a method that takes more time and be more sophisticated, and so on and so on. So it's not done all of a sudden, right? It's done in steps, cascade one. And at the end up, beyond some, you will just record the event. And then you still, as I said, 1 in a million of the one which don't keep this, you record anyway, right? Stuff like that. So it's actually very interesting because this evolves with our knowledge of what is interesting. So really, because at the beginning when we run, right, we are interested in A, B, and C. When we, after, now the triggers are very different from where the LHC triggers were at the beginning, because our knowledge has evolved, our technology has evolved. So the triggering is a very, very, very challenging and place where you can really make real progress. Right? Because now the other thing you want is to transfer the decision at the hardware level, not at the software level, right? Because it's much faster at the hardware level. So whenever you can program small CPUs in the detector themselves, that they make the decision themselves, it's much faster, and so on. And a technology on their own. Yeah, I like triggers a lot actually. So the other point I want to make is to give you an idea of what are the cross sections in the game. Okay, so let me make a table and imagine a luminosity. So the luminosity, the integrated luminosity, is measured in femtobar to the -1, or inverse femtobars. There is an I, is opposite, right? The opposite dimension of a cross section. When I multiply the cross section times this number, I get the number of events. So this is already integrated over the year, for example. So this luminosity is what we will be collecting with the run 3, at the end of run 3 and see, so nowish. And then we will collect 10 times more in the 40s, okay? In the next high luminosity run. Now, in the next year, at the end of the next year, we'll be collecting something like that. So it's really the sample of events that we have. So how many W's we will have, right? I look at the W cross section. This is around 100 nanobars. So I remember that my figure of merit is 10 Earth 4 picobar, right? Let me check again that I don't get it wrong. Exactly, got it wrong. So it's nanobar. So this figure of merit, right? This is the instantaneous luminosity at LHC. So I have 100 nanobars, and this means order of 30 10 to the 9 events. Then the Z is half of it. Then we have TT bar, which is roughly 1 nanobar. So that's the number that you want to remember, if you want. I mean, it's TT bar is 1 nanobar, which means that we'll have so almost 300 million events for TT bar. So that's why, so when we hit the millions, we say it's a factory. So when you see, when you read on the newspaper, the Higgs factory, right, whatever, Z factory, whatever, means that we are hitting the millions, okay? So we can have a statistical uncertainty of 1 per mil on a normal observable, okay? The square root of that. And then, like the Higgs, now the Higgs is 50 picobar, right? You go from nano to pico. So the number of Higgses are order of 10 million now. So it's still a Higgs factory, so to speak. So if you want this the Higgs in association with a Z or a W is order 1 picobar. So you go down further. And then you have very rare processes. Let me mention one of them, which is particularly interesting, is the double Higgs. So who heard about double Higgs production? Good. You read the news? Very good. So double Higgs production, mnemonic trick, 1,000 times smaller of single Higgs. Okay, so it's still 50, but this time femtomers. Okay, so when you had a Higgs, you lose a factor of 1,000 in cross-section. If you add a third one, you will still lose a factor of 1,000 at LHC. Okay, so it's a good mnemonics. And that tells you, right, that measuring 2 Higgses is 1,000 times more difficult, okay, than one single Higgs at LHC. Okay. Then, of course, there is another issue that somewhat we have to remember, right? That the fact that so do we see, question for you, so are we actually, when we say that they produce a Higgs at top, X and Z, double Higgs, we're actually seeing 2 Higgses in the detector? No, right? What are we saying? So let's say for the single Higgs, what do we see? What do we reconstruct, for example? Jets, very good, jets. But bosons, we have to reconstruct them also, right? So what is the easiest final state for there are 2 easy, very easy final state for the Higgs. Okay? Yeah, so there is a Higgs in 4 leptons, which is actually like Z, D star, 2 L, L bar, L, L bar. And then there is another one which is easier, which is gamma gamma, right? So this is actually the easiest one because you just have 2 gammas. then you measure the two gammas, right? And then what do? You build an invariant mass plot of all your events with two gammas, okay? So then you see that it goes down, but you actually see it and look carefully, you see that you have a big bump of events right at 125.09 GeV. Okay, and that's what we say that we see the Higgs, right? We see a peak in the invariant mass of the two photons or in the 4-lepton final state. Okay, actually this is much cleaner because the background is much smaller. Okay, so even these, there are less events. This is a much better peak because the background is much smaller than in the 4-lepton case. So what is the, so who knows what is the probability, which is, we call branching ratio, of Higgs in gamma gamma? Two? Not percent? Per mil. Ah, close. Okay, so the branching ratio is 2 per mil. And so, right, so at the end, right, every time you say that we have 15 million Higgses, well, in fact, I will have 15,000 events with Higgs in gamma gamma. Okay, so I have to multiply by the branching ratio to see the actual number of events in a given final state. Okay, so you say, well, I mean, why you're asking for gamma gamma, which has 2 in 10 to the minus 3, this is even smaller, okay, because you have to do the branching ratio of calculate the branching ratio here, and then multiply by the branching ratio squared of Z lepton-lepton, which is 3% each, so you go down very quickly. So why are you doing that? Well, I trade off what? I trade off low statistics with a clean signal with respect to a more probable final state. What is the most probable decay of the Higgs? Who knows? BB, very good. Which is, no, say? 57 is great, yeah. 57, well, it's actually 8, I think, but let's keep this number for the record. So 57, and so most of the Higgs decays into a BB bar, but the BB bar, right, the BB bar are in a detector that look like what? Jets, right? And jet is a lot of fun, but there are many jets at LHC. Basically everything, I mean, if you pick one event by randomly, it's a jet event. Okay, so the background here is huge. In fact, we don't see the Higgs alone within 2 BB bar. We are not able to see it yet because there are so many more that even a fluctuation of the background does not allow us to see just one Higgs and nothing else in 2 BB bar because the background will be huge. So this peak here is just like this. You don't see it. Okay, on the jets. But if we are actually more clever than that, right? We use other particles together. We can do it. So let me. Do you have any question? Let me complete this information now with and then I will try to stop. Otherwise, you stop me. At some point, you shoot or do something. So I want to compare with the cross section of E plus E minus. Okay. So what is the difference here with respect to this word intuitively? We'll do the formulas later, but today is intuition and numbers. So what is the difference between the numbers there and the numbers in E plus E minus? Well, as we said, a PP collider is a parton-parton collider where the energy of the parton-parton collision is not fixed. So it's like having many colliders in one, where we use statistically the distribution of energy in the center of mass distribution, natural distribution, to generate cross-section. But in plus minus, the energy is fixed in first approximation. Okay? We will discuss the fact that there is no collider where the energy is fixed. And that's actually what makes it also interesting. But anyway, let's leave. So in a leading order world, okay? Leading order means no radiation, okay? So the energy is fixed. So I need to tell you and which energy I met to tell you the cross-section. That's true also there, but there I can produce anything. But in plus and minus I cannot, right? So suppose that I have a collision, a square root of S at 91 GeV, okay, and the Z mass. I cannot produce a Higgs or Z Higgs or anything beyond the Z, right? Because I don't have enough energy, right? The energies of E plus E minus collider are way smaller, right, than the 14 TeV energy of a PP. It's a completely different ballpark. So here, for example, a Z boson, so E plus E minus to Z is about 60. I check because I don't want to get it wrong. So a 60 millibar, if I remember correctly, let's see. I wouldn't get it. Okay. Yeah, no, sorry, nanobar. I got involved by 2 order of magnitude. Okay, so these are nanobars, 60. So we have about 60 nanobars. So it's a very large cross-section. So if I have a luminosity which is high, so at this energy, the luminosity can be like 6,000 Hertz over nanobar. So it's a very large number. Then I have a square root of 200 GeV, sigma E plus E minus to W plus W minus is 20 picobar. And ZZ is 1 picobar. And the age is 200 femtobar. Now you see that the cross section goes down. It actually goes down with 1 over S, basically. Why? Because all the diagrams that we consider, so the cross section goes like 1 over S annihilation. Okay. The other thing is that the luminosity of a circular machine also goes down with energy. And the reason is what I told you before. No, I don't have the plot, I will show it. But basically, the luminosity of a circular machine also goes down with energy. So every time, so the cross section in annihilation. Why this goes down with energy? Well, because basically all diagram have let's say this one as an S-channel propagator here. So if you increase the energy, you get a suppression from the propagator in the S channel. So the cross section goes down like 1 over S. Okay. Why the luminosity of a circular collider goes down with energy? Because of this radiation that I was telling you about. It's more and more difficult to keep the bunches dense enough and in line, so to speak, to collide, the more energy you raise. So you fix the radius, you increase the energy, the luminosity goes down because it's more and more difficult to get collisions with the given energy to recover from a Brem's radiation, roughly speaking. Okay, so remember that once you have a ring for an E plus E minus, the more you increase the energy, the less events you have, and the less events you have from the physics and from the luminosity, which means that you have to run longer to recover from it. Okay? So that's the reason why, right, the cross section goes down very fast, and also the luminosity goes down very fast. So both of them are important. So an FCC-EE, okay, so the future collider that we will build at CERN, we will have 10 to the 5 Z's per second, 10 to the 4th WW per hour, 1,500 X a day, and 1,500 tops per a day. I didn't write the top one. Okay, so you see the advertisement way of keeping these numbers high, right, and increasing the span. Okay, but you see that, I mean, it will be very easy. So who knows how many Z's were produced at lab 1? Ballpark? Recorded, not produced, yes. 10 to 2 in 10